everyone, and thank you for watching this video. My name is Alexandra Denoy, and currently I'm a part of the Optimum Solutions Backwork program. However, the bulk of my year I'm an electrical engineering student at WITS. And today I'll be attempting to demystify deep learning with specific reference to the concept of semantic segmentation. To start off, let's look at what will be discussed. A trilogy of topics, if you will. Where deep learning went right, some more of deep learning's best techniques, and what is this deep learning thing anyway? Though these topics still have a lot of information to be discovered, don't panic, we're going to get there. What is this deep learning thing anyway? Well, deep learning is a branch of machine learning involving training models to analyze data, often audio, image, and video data, and then extract features from it. The main difference between traditional machine learning and deep learning is that deep learning works to perform this feature extraction automatically. That is, we could give a model an image like this, and it will look for features like edge detection that might allow it to make a prediction or decision. This is all done without interaction from the user. Most importantly, deep learning done right is accurate, and accuracy is very important. It's sometimes more accurate than people, though the impressiveness of this feat is definitely person dependent. Well, we know what deep learning is and we know it's accurate, but why do we care about that? The fact is, people are prone to error and difference in opinion, and in some fields, like the health field, this can be a safety risk. Deep learning not only allows us to perform tasks correctly and objectively, but quickly. Again, why do we care? Well, automation, 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 over a broad range of fields. For example, one of these is medical research. The image presented here shows slides of tissue and is focusing on the classification of colon glands. Here the hand labeling is presented in green and has been performed by a specific person, and the model has labeled or classified the glands in blue. We can see that the two are fairly similar. Why is this important? Well, if we applied this to, say, cancer research, we might be able to use deep learning to find malignant tissue earlier and more quickly, allowing people to gain access to treatment faster. A second example, something we'll be looking at quite a lot today as well, is that of automated driving. Here, deep learning models are used for object identification, such that a car might be able to respond correctly to a specific situation. So, where has deep learning then been all my life? Well, the concept of deep learning has been around for quite a while, and papers describing the concept have been written extending to 1986. However, there are a set of enabling factors that have made deep learning more accessible today. These include shared resources, increased computing power and computing techniques, as well as something known as the pre-trained network, which we'll look at further. Where did deep learning go right? Well, perhaps went right is not the correct phrase, but there are certainly features of deep learning that have made it easier for the less experienced user. One of these is the concept of transfer learning. Transfer learning involves taking a pre-trained network, which could be trained on completely unrelated data, and building up further on its current capabilities, and then applying it in a different context. This means we need far less training data and far less training time before we can start using a model in a given application. So to implement transfer learning, the workflow pictured here must be followed. Let's go through each of these steps. Step 1 involves loading a pre-trained network. So deep learning makes use of convolutional neural networks, and these networks have many hidden layers. Each layer within the network applies a different feature extraction technique on the original input. The results of each layer are then used as an input to the next layer. When we load our pre-trained network, the feature extraction layers have already been formed through all its previous training. Step 2 involves adjusting the last layers of the network. The last layers are known as classification layers and involve combining all the results of previous layers such that the model can then make a prediction or classification. These layers are what we adjust so that we can apply our network in a specific context. Step 3 of transfer learning involves actually training our network with specific application images. One step not listed here is that often our images need to go through quite a lot of significant pre-processing before we can use them. Step 4 looks at predicting the accuracy of our network and determining whether the model is suitable for deployment. And lastly, we need to deploy our model into our specific application. So now let's focus on an aspect of deep learning, or one of its techniques, known as semantic segmentation. This process is used to take an image and label its pixels according to a set of categories. Each category then gets given a specific color, and these color labels can be overlaid on an original image. For example, if you're considering cell diagnostics, the image on the left might be labeled like that on the right, such that sickle cells are clearly visible. Again, if we consider automated driving, this original image on the left could be labeled like that on the right, such that certain features like buildings or cars can be presented in specific colors. But why is this an important process? Well, there are many applications that need these labels for object identification. Before deep learning, these kind of images would have to be hand labeled, as is being done in the video showing. As you can see, it's not a particularly efficient process. However, with deep learning, the model is able to automatically label images. This reduces the amount of time required to produce these labeled images and frees up the original user. To understand this concept more in depth, I will use a MATLAB demo to continue the idea of automated driving. To start our example, we'll be loading our pre-trained network. The example we're using is based on a SegNet system and an original pre-trained network known as VGG16. This is quite a nice network because it's trained on more than 1 million images, and this is definitely 1 million more images than we currently have access to. To make sure you have this ability to use VGG16, just make sure that it's downloaded and installed. Our next step is that of pre-processing our images, but to do that we first need images to pre-process. I've acquired mine for this context from the 2 URLs depicted here. The first one, the top one, is the images, and the second one are the corresponding labels. When you download them, just make sure that your output folder over here corresponds to where your images are saved. So we have our images. The next thing we need to consider is their effect on memory. Obviously, there are a lot of them, and they're quite large, and they take up a lot of memory. So we're going to use a function here, this helper function prepare data, and this basically reduces our image dimensions by half, and this just decreases our total memory usage and speeds things up a little bit. Now that we've reduced our image size, we need to consider how we're going to manipulate all our images. Obviously, again, we can't have them all in memory, so we store them in an image data store, and this allows us to have full access to our images. Let's look at one of the images we have access to. This is a raw image. You can see a normal city street with people and roads, and this is the same image just after a bit of manipulation. This just allows us to see some of the features more clearly. What we need to consider next is the categories that we'll be using. So the SegNet system has 32 predefined classes. However, we only want to work with fewer. So we take the 32 classes and we group them according to these categories. And each one of these classes or categories is given a group ID, and each group ID is given a specific color. So this allows us to take images and the labels and create a picture like this. So you can see here pedestrians are in brown, and buildings are in red, and things like trees are in green. Another aspect to consider when training your network is how balanced the classes are. So, for example, if we look at the frequency of pixels from each class throughout all our images, those in the classes of road and building and sky appear a lot more frequently than those of poles or pedestrians or fences. This is something we have to take into account because classes that are rare are more difficult for the model to learn. Our next step involves setting our training and test sets. Obviously, we don't want to use the same data for training and testing, and we tend to split this randomly in a 60% 40% split. One of the final steps before training is that of data augmentation. This involves randomly rotating or reflecting or translating the images we have to basically synthetically produce more training images. This is important because the more images we have, the more accurate our network can be. We now move on to step 2 of the transfer learning workflow, and this involves manipulating the classification layers. So we use something called segnet layers, which basically takes the network architecture that is currently there for VGG16 and makes it appropriate for semantic segmentation. We end up changing the last layer of our network, and this is so that we can take into account our new classes and our class weights. So this goes back to the imbalance we saw earlier. Basically, the classes that have high frequency, we assign low weights, and this allows us to balance our training data more effectively. If you look at this image here, initially the last 9 layers are depicted like this, and if you look at our new last 9 layers, you can see that we've changed the last layer here to what we've called labels. We can now move on to step 3 of transfer learning, and this involves actually training our network. The first thing you do is set the training options. While I'm not going to go through them, you can read about each one of them in the commented code here. They obviously all have an effect on training time as well as accuracy and should be optimized for the application. If you want to actually train your network, the command you can use is this one over here. However, unless you'd like to sit with me on this webinar for 19 or so hours, or plausibly more, but to not do that, I'm going to just use one that's already been trained for this context. We can now look at the results of using our trained model. As you can see here, this image on the left is one that has been labeled by hand, and the one on the right has been labeled by the model. It's obviously not as clearly defined as the one labeled by hand. For example, we can't differentiate between individuals, we kind of just see them as a blob. However, for the context of automated driving, a car would definitely be able to recognize that these are people and it shouldn't drive there. In this case, we've only done a visual comparison between the model and the labeled image. However, if you do want something more numerical, you can use something known as the Jacquard index or intersection over union. And this shows how well the two overlap in terms of the specific classes. There are, as well, though I'm not going to show it, other metrics that you can use to determine the accuracy of the model. So this includes, or this acts as part of step 4 of our transfer learning workflow. And moving on, we can discuss a little bit about step 5, which is deploying our final model. So now that you've trained, you can move on to deployment. Something we need to consider is where our model is going to be implemented. So is it going to be on a chip or device without MATLAB, and whether it needs to be able to perform real-time processing. If this is something that's important, you might want to consider using a GPU. This is because GPUs have a lot more cores and parallel processing capabilities. But how do we use a GPU? Well, fortunately, MATLAB has something called the GPU coder, which is able to automatically generate CUDA code from MATLAB code you've already written. This can be done using the GPU coder, and there are many tutorials online that involve how to use this. So if that's something you want to look at, I definitely suggest checking it out. So what's next? Finding the meaning of life. It's 42, by the way. However, if you're sitting there going, life, don't talk to me about life, tell me something useful, well, here are some useful next steps. I suggest looking at more content, whether it be about deep learning or generating CUDA code, or just something else that's interesting. You can often find this at the Optimum Tech Corner. If you want to try these examples yourself, you can do the deep learning on-ramp, or you can ask Optimum for a trial. And if you need more support, Optimum Solutions is capable of supplying the tools and training, whether it be personal or online, or consulting if you need help in any specific application. So this concludes the presentation, and thank you for watching.